Hello everyone and welcome to the ROS2 tutorials. In this tutorial we explain how to model and simulate a four-wheel mobile robot in ROS2 and Gazebo from scratch. In our previous tutorial we explained how to do the same modeling task in ROS1. However, it is far from trivial to generalize the ROS1 implementation to the ROS2 implementation. Namely, to model the robot in ROS2, we had to write a completely new launch file and to significantly modify the Xacro model files, such that the model could be properly displayed and simulated in Gazebo. Furthermore, the process of building the workspace and packages in ROS2 is completely different from ROS1. Briefly speaking, in this tutorial you will learn how to model the robot that you can see over here, and how to define and utilize a controller that will enable you to move the robot by using the keyboard keys. For example, in this terminal over here you can see the keys, or better to say the letters that you need to press in order to move the robot. For example, if I press the letter K, the robot will stop. Then, if I press J, the robot will rotate in counterclockwise direction. Then, again, if I press K, the robot will stop. If I press L, the robot will rotate in the clockwise direction. Then again, if I press K, the robot will stop. Let's see other options. I have I. Let's see what I is doing. If I press I, the robot moves downward. Very interesting. Then if I press M, I obtain this motion. And you can experiment later on, once you model the robot. At the same time, in another terminal, given over here, you can obtain more information about the type of messages that are being sent through a topic by typing, for example, ROS2 topic echo, and let's, for example, echo the odometry messages. And if I press this, you will see the odometry over here. Now let me expand this so you can better see it. So these are the twists, linear, angular, and you can even see the covariance. This is very useful. Before we start with implementation and modeling, we need to mention a few important things. First of all, this is a self-contained tutorial, and we explain all the necessary modeling steps. You need to carefully watch the complete tutorial and to implement these steps. By typing what we are typing and by following our explanations, you will be able to reproduce the complete model. However, we also provide a complete manual and modeling files explained in this tutorial. A link to the manual and files is provided in the description below this video. You should keep in mind that we spent a significant amount of time on creating this tutorial and the manual. Secondly, this is a long tutorial since the modeling process will be explained thoroughly. If you skip some of the steps, you will not be able to reproduce the model. Consequently, reserve some time to watch this tutorial and to understand what we are typing and explaining. As mentioned previously, the tutorial that you're currently watching is self-contained and we thoroughly explain all the modeling steps. However, if you're completely new to ROS or completely new to ROS2, then we strongly suggest you that you go over our previous tutorials. And here are the 3 tutorials that are very important for the tutorial that you're currently watching. In the tutorial that you can see over here, you can learn how to create URDF and launch files in ROS2. Then, in this tutorial, you will learn how to write launch files and how to load URDF or Xacro model in Gazebo and ROS2. And finally, this is a ROS1 version of the tutorial that you're currently watching. Links to these tutorials will be provided in the description below this video. Okay, let's start with explanations. In step number 1, we need to verify that we have the correct version of Linux and ROS2. Namely, everything explained in this video tutorial will work under the assumption that you have Ubuntu 22.04 and that you have ROS2 Irwini. Let us verify the Linux distribution. To do that, open a new terminal. You can do it like this. Click on terminal, and in the new terminal you need to type this command. Let's expand this window. And you can see over here that I have Ubuntu 22.04, and this third number actually doesn't matter. It can be anything. However, the most important thing is that you have 22.04. Perfect. Let's continue. Let's verify the ROS version. To do that, first of all, we need to source the environment. So go back to the terminal and execute this command. After that, you need to type this. And you can see that in my case, the result is iron. This means that I have Iron Irwini installed on my computer. And this is ROS2 version. Step number 2 is to install the necessary packages. Let's do that. For that purpose, I will open a new terminal and I will start typing. Every time you want to do something with ROS2, you need to source the environment. Consequently, you need to source this setup.bash file. So let's do that. Okay. Then we need to install the necessary ROS2 and Gazebo packages. Some of these packages you might have. However, it's still an excellent idea to try to install them. If you already have them, the installation attempt will not change anything in your system. So don't worry about it. Here is a list of installation commands that I need to execute. And let's do them step by step. Okay, first let's do this. You need to enter your password. Okay. And you need to be patient. Of course, patience is the most important virtue when you code and when you deal with ROS2. Okay, next let's install gedit. And as you can see over here, gedit is already installed on my system. And most of these actually packages are installed. So you will see over here 0 upgraded, 0 newly installed. However, in your case, you might see the installation progress. Then let's install this part, or better to say this ROS package. Then we need to install this one. Then you need to install this package. Okay. Next, we need to install Gazebo packages. Then you need to install this one. And let's continue. Let's go to the next page. We need to install this package. Then we need to install this package. Then we need to install this package. Then we need to install this very important package that will enable us to control our robot by using the keyboard keys. And finally, this is another very important package for controlling the robot by using the keyboard keys. Okay, next, let's verify that the Gazebo is properly installed. To do that, we need to type Gazebo. And after some time, you should see the main Gazebo window. Here it is. This means that we have properly installed Gazebo. And these commands are actually installing the Gazebo on your system. Now you can safely close Gazebo. Another approach for verifying that Gazebo is properly installed is to type this. And you can see my version of Gazebo. Perfect. In the step number 3, we need to create our workspace and the package. And let's close these two terminals. And let's open a new terminal because I always like to start from scratch. This is a very good practice. Let me change the size of this terminal and let's continue. Again, the first step when you do something in ROS2 is to source the environment. This is actually called creation of an overlay. Okay, then let's create the workspace folders. To do that, we need to type this. This command will actually create in our home folder, and the symbol for home is tilde, this folder called WS Mobile, and inside of that folder we will have another subfolder called source. So let's do that. Next, we need to create and build our workspace. To do that, we need to change the working folder. Consequently, we need to go to our workspace folder. And in ROS2, you can build a workspace by executing this command. Okay, perfect. We initialized our workspace. Next, let's create the package. To create the package, we need to go inside of the source folder, inside our workspace folder, and in that folder, we need to execute this command. ROS2 package create. Here we specify an additional parameter, and the most important thing is the name of our package. I will call the package mobile robot. My suggestion is not to change the name of our package. That is, don't change mobile robot. Later on, when you become more proficient, you can give your own names to the packages. However, in this tutorial, strictly stick to this name. Okay, so let's execute this command. And here it is. Perfect. Let's continue. Next, let's navigate to our package folder. To do that, we need to type this. And inside of the package folder, let's create two additional subfolders, launch and model. Let's explain these two folders. The launch folder will contain the Python launch file necessary to run the model in Gazebo. The model folder will contain the Xacro and URDF source files of the model, as well as a Gazebo empty world model that is used in an environment. Actually, in this tutorial, we are not going to create an empty Gazebo world model. However, you can easily create that model if you wish. The tutorial will work perfectly without a Gazebo world, since we will be using the default Gazebo world. Note that the URDF stands for Unified Robotics Description Format. This is a file format that's used to specify the geometry of robots and some other properties. Xacro is an XML macro language used to parameterize and simplify the URDF model development. Next, let us build the complete workspace once more. To build the workspace, first we need to go to the workspace folder, and inside of that folder we need to execute this command. And here, let's see. Perfect. In step number 4, we need to create the URDF or Xacro and Gazebo files. First, we will create the robot model. We create the robot model by creating two files, Xacro and Gazebo files. The first Xacro file contains the 3D model of our robot, and the second Gazebo file contains additional parameters necessary to successfully represent and control the model in Gazebo. First, let's navigate to the model folder. And inside of the model folder, let's create the Xacro model file. We do that by calling the G editor. The name of the file is robot.xacro. And here it is. It's an empty file. Over here, in the interest of the brevity of this video tutorial, I will simply paste the content of the file, and I will explain the file line by line. I will save it, and I will do an additional thing. Namely, it's kind of difficult to explain this file by using gedit. Consequently, I will close this file and I will open it from another editor that's more suitable for representing these long files. However, you should definitely type your file in gedit, or of course, if you know some other option for typing that's more suitable, you can use it. Since I saved this file, I can close the gedit. Then you can see the terminal is active. Next, I will open a new terminal and actually I will start my favorite editor that's called Spider. I have a separate video tutorial explaining how to install Anaconda and how to install Spider. Over here, in the interest of brevity, I will simply start my Anaconda navigator. I need to type this, and you need to do this. You need to type Anaconda navigator. Again, I have a separate video tutorial explaining how to install Anaconda. Again, you don't need Anaconda for this video tutorial. Okay, and over here I will start my favorite editor. It's called Spider. I'll click here on cancel and I will open our file. I will close these two files and over here I need to open file, open, and I need to find it. It's in my home folder. Here's the source, then it's here, here, model, and over here I need to specify all files, right? So I need to find options for all files and I need to open it. And here it is. It's easier to explain this file by using this editor, since it's quite a long file. This file might look long, however, there is a pattern inside of this file and some parts are actually repeating with few parameters that are changing. So let's start from the very beginning. Every Xacro or URDF file starts with this. So you shouldn't touch this part. This is very important. Then we write comments like this. We use this tag environment, we start the comment and we end the comment. So the lines 2, 3, 4, 5, and 6 are actually comments. Next, we arrive at the line number 8. Over here, we start the tag, robot, and if you scroll down, all the way down, 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 you will see end of the tag. So everything inside of this robot tag that starts with robot and ends with robot is actually the model description. Let's analyze this tag. Over here we specify the name, differential drive robot, and notice that this name will also repeat in some other files. And over here you can simply type this part and don't change this part. Here is a geometrical description of our robot. The robot consists of the robot base and 4 wheels. First, second, third, and fourth. The base and wheels are called links in the ROS terminology. Between the robot base and wheels, we have 4 joints. These joints actually enable wheel rotation. That is, in a ROS URDF or Xacro files, the robot geometry consists of links and joints. So what is a link? Link is body, then the link is this wheel, this wheel, this wheel, this wheel, and in between the links we have joints. So the joints are over here, over here, over here, and over here. This top view defines almost all geometrical parameters except for the z-axis locations of the center of the wheels and the z-axis height of the robot body. The centers of the wheels are at z equals to minus 0.1 and the z-axis robot height is 0.3. That is, the thickness of the body is 0.3 and the center of the wheels are located at z equals to minus 0.1. The center of the body is at 0, 0, 0. So this is the global coordinate system of the first frame. And the robot bottom surface is at z equals to minus 0.15, and the top surface is z equals to 0.15. Now that we understand the robot geometry, let's go back to our Xacro file. Over here we specify the body dimensions. And for that purpose we use this tag, or better to say this macro, where we can actually parameterize the dimensions. We introduce the variable body length x dimension and we specify the value. By doing this, we parameterize actually the body length x dimension. And you will see later on in the formulas, instead of this value 1, we will just use this name. This is a very convenient approach if you want to completely parameterize your model. You don't need to change the numbers over here. You will just change the values over here and they will be automatically updated in your file. Okay, so we have body length x dimension. Let's go back to our description and here it is. This is the x dimension. And you can see the value is 1. Similarly, we define a variable called body length y dimension, or better to say a parameter, and the value is 0.6. Aha! Where is 0.6? Here it is. This is the y dimension. Perfect. How about the z dimension? Body length z dimension, and the value is 0.3. This is actually the dimension that you cannot see on this graph. This is the dimension in the direction of the screen. Perfect. Now we covered everything until the line 15. The line 15 is simply a comment. And over here we define the wheel dimensions. Let's go back to our sketch. Here are the wheels. So what are the dimensions? 0.1 and 0.3. Aha! Let's go back to our Xacro file. We can see the radius is 0.15. The radius, here you can see the diameter. Half of that is the radius, that is 0.15, and we can see 0.1, wheel length. And you need to specify another parameter, wheel length z location. The center of the wheel is actually at minus 0.15. This is very important. Next, let's define the material density. Again, we are using this macro, or better to say parameter. I call it body density, and I specify the body density in kilograms per meter cube. And just to clarify one important thing, all the variables over here, or better to say the units of these variables, are in meters, kilograms, and in other SI units. Okay. Here we specify the body density and we specify the wheel density. Of course, you can change this density. Next, we specify our pi constant. And I use 1, 2, 3, 4, 5, 6, 7, 8 decimals. However, you can also use 3.14 if you want over here. Line 27, we need to specify the robot body and the wheel mass. There are two approaches. You can use the values that we define over here, 1, 0.6, and you can manually calculate on the basis of the density. You can calculate the mass. However, that's an approach that it's not suggested, right? Don't do that. Use the parameters, and that's precisely what we are doing over here. We specify the name body mass, and now you can see the power of the parameters. Here the value is equal to, then you need to, under quotation signs, then you have a dollar sign, and over here you start a formula and you simply write the formula for the body mass. That depends on the density and depends on the volume. The volume of the box is body length x dimension, body length y dimension, body length z dimension, multiplied by the body density, and that's it. Then we define the wheel mass. You start the tag name, wheel mass, value, and then over here formula. It's simply the mass of a cylinder if you give me the density of the cylinder and the dimensions of the cylinder. And that's it. Simple as that. After we specified the robot body and the wheel mass, we need to define the moments of inertia. Here you need to stop for a second. In order to simulate the dynamics of the robot, you need to specify the moments of inertia. And this is very important. So how to do that? Again, we use the parametric approach. Here is the moment of inertia of the wheel with respect to the z-axis, and this is the local z-axis, and here's the formula. The moment of inertia depends on the wheel mass, wheel link radius, squared, right? Then, we need to specify the moments of inertia around two other axes. Since the wheel is symmetric, we will actually have only one axis, and the second axis will be equal to that axis. Better to say, the moments of inertia of the two axes will be equal. And here's the formula. Next, we define a macro that defines the complete inertial section of the wheel. And here it is. This is very important to understand. Namely, later on in this file, we will have to model every wheel. And for every wheel, we will need to specify the moments of inertia. And essentially, we will have to write this block for every wheel. And then you have 4 wheels, 4 times these blocks. You will have to write 4 times, and the file will be cumbersome. Instead of doing that, we can define a macro. And we can specify the macro name, inertia wheel. Then, later on in this file, when we specify the inertia of the wheel, we will simply type inertia wheel. And the interpreter will automatically look over here, and the interpreter will find the correct values of the parameters. So how we do that? We start this tag, we end the inertial tag, then we specify the origin, we specify the mass value, and we specify the inertia. And you can see over here Ixx, Ixy, Ixz, Iyy, and Izz. These other moments of inertia are 0 because the wheel is symmetric. And this is very important. This part from here until here defines the model parameters. Okay, now let's proceed further. Over here, with this line, we actually include a file that defines extra gazebo options and a very important motion control driver. We still didn't create this file. We will create this file later on in this video tutorial. However, it's very important to include that file inside of our Xacro file. The name of that file will be robot.gazebo, and it will be located in the model folder. This is very important. Next, we define links and joints. Over here, we need to define this dummy link. And if we don't do that, Gazebo will complain and Gazebo will not be able to properly load the model. So how do we define links? We open the link tag and we end over here the link tag. And we give the name to our link. It's called dummy. Next, we need to define a joint. Here's how we start the joint and here's how we end the joint. I will call this joint the dummy joint. The type is fixed since I'm not rotating this joint. The parent link for this joint is actually our dummy link, and the child link is our body link. We will define the body link in the sequel. Here, it's very important to keep in mind the following. This type of modeling language uses this principle. You will always have a parent link and a child link of a joint. This is very important to keep in mind. For example, in this case, if the joint is between wheel 1 and body link, then for this joint, the parent link will be body link and the child link will be wheel 1 joint. So that's the principle. Keep in mind that. Over here, we start the body link of the robot. We open the link tag, and somewhere over here, we need to end the link tag. We end it over here. Open on 68, end on 92. We specify the name of the link. I will call this link as body link. Over here, we specify the visual representation of the link. Inside, we have geometry tag. We specify the box size, X, Y, and Z dimensions, X, Y, and Z dimensions. Keep in mind the graphical representation. We specify the origin, and we end the visual tag. Next, we need to specify the collision box. The collision box is actually identical to our geometry. No big differences, or better to say, identical to the visual representation of the robot, so don't change this part. And over here, we need to specify the inertial properties. We start the inertial tag, we end the inertial tag. Inside of this tag, we need to specify the origin, mass, and we need to specify this long inertia tag. We specify IXX, IXY, IYY, IYZ, and IZZ moments of inertia. Basically, this is a tensor of inertia. We close inertial and we close link, and that's it. And this was the body link of our robot. Next, we need to specify the back right wheel of the robot and the joint. Where is the back right wheel? Let's go back to our description, and here's the back right wheel. Okay, so let's specify this wheel. The name of the joint connecting the body and the back right wheel is wheel 1 joint. The type of the joint is continuous. Now we need to specify the parent link. The parent link is obviously the body link, and the child link is wheel 1 link. Where is wheel 1 link? Here's wheel 1 link. This is very important. Let's continue. Next, we need to specify the origin. And over here, I will move the cursor so you can completely see this line. Or let me zoom out. I think that might be the better option. So here it is. Here we specify the origin, and you can see that everything is parameterized. Then we specify X, Y, Z, and we specify RPY. RPY are the roll, pitch, and yaw. And we don't have any rotation, consequently it's 0, 0, 0. Again, let me zoom in so you can see it until here, and then I will move this so you can see the other part. Here it is. Next, we need to specify the axis, X, Y, Z. Y is equal to 1. Let's look at the graph. And you can clearly see that the y-axis is oriented like this. This is very important. Here we are specifying that this joint will actually rotate around the y-axis. This is very important. And over here we specify additional parameters: limit effort, velocity, dynamics, damping, and friction. You can actually play with these parameters. And we end the joint environment, or better to say joint tag. Perfect. Let's continue. Now we have defined the wheel 1 joint. We need to define the wheel 1 link, and the procedure is the same as in the case of defining the body link. We specify the name, wheel 1 link. Here it is, wheel 1 link. Then we specify the visual representation, we specify the origin. Here we have rotation, RPY, and the rotation is in radians. That is, the coordinate system is rotated with respect to the coordinate system of the joint, or better to say of the body. And we specify X, Y, and Z. Over here is the geometry. It's a cylinder. Our wheel is a cylinder, wheel link length, and wheel link radius. We end the geometry tag, we end the visual tag, and we start the collision tag. And here's the collision tag. Collision tag is simply copy and pasted the visual tag, and that's it. And we end over here. Actually, before we end, we specify one very important part. That is, we specify the inertia. And what do we do over here? Now be careful. We actually write inertia wheel. And actually this is a macro. And this macro is actually defined over here. So when we wrote inertia wheel, the interpreter took this part and inserted this part instead of this name over here. And this is how we can simplify the file. And this is the end of the back right wheel of the robot and the definition of the joint. Perfect. Next, we need to define the back left wheel of the robot and the joint. Wheel 2 joint. Let's see where is wheel 2 joint. Here it is. This is the wheel 2 joint, or better to say its frame. And we have wheel 2 link. Let's define these two objects. Again, we specify the joint name, type is continuous, we specify the parent link, we specify the child link, we specify the origin. So again, I will zoom out this part so you can see what's happening over here. Nothing special, you can already see the pattern. Here's the origin of the coordinate system, X, Y, and Z, and roll, pitch, yaw, no rotation. And you can see the axis. Since our wheel will rotate around the y-axis, that is around this axis, over here you need to specify 0, 1, 0. And you need to specify the limit effort. Velocity, dynamics damping, friction. And you end the joint tag. Again, I will move my cursor so you can better see this line over here. Here it is. Next, we need to define wheel 2 link. So where is wheel 2 link? Wheel 2 link is over here. Let's define wheel 2 link. We start the visual environment and you can already see the pattern. Here where the origin is, we start the geometry, we end the geometry, we end the visual representation. The collision tag is simply copy and paste of the visual tag. So no differences over here. And again, over here we are calling the macro inertia wheel. Again, the interpreter will go back at the beginning of our code and it will simply insert the inertia properties. And that was the back left wheel of the robot and the joint. Next, we need to define the front right wheel of the robot and the joint. So let's do that. Where is the front right wheel? It's the wheel 3 joint, wheel 3 joint, and wheel 3 link. Okay, so let's define them. Not a big deal. Again, there is a pattern. Name, type, parent, child, origin. Again, let me move the cursor, or better to say scroll right, so you can see this line, and zoom out so you can better see it. Here it is. Then we specify the axis. The rotation axis is the y-axis. We specify the limit effort. We specify the velocity. We specify the dynamics damping. And we specify the friction. And we end joint. Next, we defined wheel 3 link. Where is wheel 3 link? Well, wheel 3 link is over here. Again, visual representation, origin, R, P, Y, roll, pitch, yaw. We have a rotation of coordinate systems. We have geometry. Geometry is, of course, a cylinder. Then, this is the visual representation. The collision is simply copy and paste of the visual. And over here, again, we call the macro inertia wheel to specify the inertia of our wheel. And we end the link. That was the front right wheel of the robot and the joint. And we are only left with the front left wheel of the robot and the joint. Okay, so let's look into our graph. We need to define the wheel 4 link and the wheel 4 joint. So let's start with the joint. Again, the pattern, name of the joint, type is continuous, parent link, child link. Here's the origin. Again, I will zoom out, although you can already see the pattern over here. Then you can see the axis, limit effort, velocity, dynamics damping, friction, and the joint. And finally, let's define the link. Link name is wheel 4 link. Here it is. Visual representation, origin, roll pitch yaw. We have rotation in radians again. Geometry, here's our geometry. Visual representation, here's collision. Again, collision, copy and paste. The visual representation, and over here we called the macro inertia wheel. And that's our link. And that's the end of the front right wheel of the robot and the joint. And finally, we end the Xacro file with closing the robot tag. And that's it. Simple as that. Although this file is 240 lines, this file is actually not complex. And again, I will slowly scroll down this file so you can see everything again. This is relatively easy. This is not hard. Don't be afraid of this file. However, you need to model the robot. This is very important. If you create a mistake over here in this file, then you might have issues and you will not be able to compile the robot. My advice to you is to actually write a minimal file and then try to compile everything. To do that, you can actually follow one of my previous video tutorials, whose link is given in the description below. Before we actually close this file, it's very important to once more briefly revise and explain this line. This line is used to include this file, robot.gazebo. However, we still didn't define this file. This file will contain additional gazebo parameters that are necessary to simulate the model. Our next goal is to define this file. You can safely close .robot.xacro and go back to the terminal. In the terminal, you need to type gedit robot.gazebo. To make this video tutorial as brief as possible, I will simply copy and paste the content of the file, and I will explain the file line by line. Here it is. The first line specifies the version of the file. Then, I here have 1, 2, 3, 4, 5, 6 comments, and over here the robot description starts by opening this tag, and at the end of the file we close the robot tag. Don't forget that every time you open a tag, you need to close the tag, unless it's an inline tag. Okay, so let's see what's happening over here. Over here, I provided you a link to a description of mu1 and mu2 parameters. These are the so-called friction coefficients. Over here, we define gazebo properties for the body link. We open the gazebo tag, we close the gazebo tag, and we specify the friction parameter 0.2, 0.2. You can change these values and you can experiment. And finally, we specify the color of the body link. In my case, it's red. Next, we define the gazebo properties for the wheel 1 link, mu1, mu2, and we specify the color. The color is yellow. We do the same for the wheel 2 link, mu1, mu2, color, for the wheel 3 link and the 4 link. That is for the wheel 4 link. And that's it. Next, we need to define the controller for the 4-wheeled robot. So what's the purpose of the controller? The controller will take the keys that are pressed on our keyboard, and it will convert them into the motions of wheels. To define our controller, we start the gazebo tag and we end the gazebo tag at the end. Inside of the gazebo, we need to specify the plugin. The plugin name is Skid Steer Drive, and the file name is specified over here. This is actually a file name in Gazebo library. So we are using one of the standard controllers from the Gazebo library. Notice over here differential drive. Well, this controller is not a differential drive controller, however, the file is the same for the differential drive robot and the four-wheeled robot. Over here we leave this namespace tag empty, since we are not going to play with namespaces in this video tutorial. However, it might be a good idea if you have several robots to assign a namespace for every robot. Next, we need to specify number of wheel pairs. We have 2 pairs of wheels, front and back. Consequently, we specify 2 over here, and we specify the wheels. That is the pairs of the wheels. Left joint, right joint for the first pair. The first pair will be, in our case, this pair over here. And consequently, we specify the properties over here. We say that left joint is actually wheel 4 joint and the right joint is wheel 3 joint. Then we define the second pair, wheel 2 joint and wheel 1 joint. Okay, here it is, wheel 1 joint and wheel 2 joint. This is very important. Let's continue. Next, we need to specify kinematics. We need to specify the wheel separation. And here's the formula. Notice over here that we are actually using the parameters defined in the Xacro file. We can do that because this file will be eventually placed inside of our Xacro files. So what is the wheel separation for the first and the second one? Well, you simply need to look into the graph, and it is body link, y dimension, wheel link length, and that's it. And we need to specify the wheel diameter for the pairs, front and back pairs. Here they are parameterized, and we need to specify the limits. We need to specify the torque limit, we need to specify the max acceleration of the wheel. This is also another important thing. You can play with these parameters. Next, we need to specify the output. So what are we publishing? We will be publishing odometry TF, and wheel TF. So we are publishing these 3 messages through the corresponding topics. And we need to specify the odometry frame. It's called odom. And we need to specify robot base frame. It's simply a dummy. And that's it. This is exactly the dummy frame from our Xacro file, and this is very important. We end the plugin, and know that the plugin is started on the line 46, it's ended on the line 83, we end the gazebo tag, and we end the robot tag, and that's it. Simple as that. Let me again scroll down this file so you can nicely see it. And that's it. That's our robot.gazebo. Let's continue. You should save and close the previously defined file. In step number 5, we need to create the Python launch file. We create the Python launch file in the launch folder. Consequently, we need to go, or better to say to navigate to that folder. We do it like this. And inside of this folder, we need to define this file. The name of the file is gazebo_model.launch.py. And here it is. Again, to save time, I will simply copy and paste the content of the file over here, and I will explain this file line by line. I will save this file, and I will actually close this file from this editor, and I will open the file from my Spider. Why I'm doing that? Well, I noticed that gedit sometimes doesn't properly align the tabs of the Python files. And this is very important. If the tabs are not properly aligned inside of functions or inside of the loops, you might not be able to compile that file. And this is very important. This is why I'm also using Spider to verify my files. And I will use Spider to explain the file. The file is located over here. Here it is. And I will zoom in. And let's start with the first line. Over here we import Python library ROS. Then we import several libraries and modules. They are actually ROS and Python modules and libraries. And over here we import Node and we import Xacro. This is very important. This file contains a single function starting at the line 12 and ending here. This function will return the launch description object, and we will define that object inside of the function. Over here you need to specify the names. First of all, you need to specify the robot Xacro name. This is the name of the robot in our Xacro file. The name of the robot is differential drive robot. Let's verify that this name is correct. To do that, let's open our Xacro file. Xacro file is actually over here. And we need to select all files. Here it is. Okay, so here it is. Robot name is differential drive robot. And over here, this name matches the robot Xacro name. Perfect. Next, we specify the name of the package. The name of the package is mobile robot. You remember at the beginning of this tutorial, let me open up the file. Over here, we created the package, and the name of the package is mobile robot. Consequently, in this file, you need to use the same name. Then, you need to specify a string that defines a relative path to the Xacro file defining the model. It is model robot.xacro, and the relative path is with respect to what? The relative path is actually with respect to the mobile robot. Keep in mind that, that's very important. And you need to define the world file relative path. Here it is. In this case, we are not using actually the world file, however, still we specify it over here. In some other implementation, you can define your Gazebo world file and you can enter it over here. However, I'm not going to do it in this video tutorial in order to make this video tutorial as brief as possible. Next, we need to define the absolute path to the model. For that purpose, we use this function os.path.join. We now use this function. We specify the name of the package and we specify the model file relative path. Next, we specify the absolute path to the world model. We do it like this in the same manner. Next, this line is very important. This line will actually read the robot description from the Xacro model file, and we will process the file. Over here we need to specify the path to our file, and we call the function to XML. Good, let's continue. Over here we specify the launch file from the Gazebo ROS package. That is, this is not the file that we actually defined. The name of that file is gazebo.launch.py, and we are actually automatically extracting a path to the Gazebo ROS package over here, and we add a few things. That is, we define the absolute path. This is the launch file description. Here it is. We use the previously defined path. We specify the arguments, world, path to world file, and we specify items. Over here we actually have a dictionary. Here, we create a Gazebo ROS node. We call the function node, we specify the package, Gazebo ROS, executable is this one, and here are the arguments. We specify the robot description, then we specify the entity, robot Xacro name. Where is the robot Xacro name? Let's go back. Here it is differential drive robot, and the output should be screen. This is very important. Over here we define the robot state publisher node. The package is robot state publisher. Output executable is robot state publisher. The output should be screen, and here are the additional parameters. And here it's very important to use this parameter, use simulation time, and to specify the value to be true. Over here we create an empty launch description object. Then we add Gazebo launch, and we add two nodes. This one defined over here, and this one defined over here. And that's it. And we finally return the launch description object. That's the whole file. I created a separate video tutorial that explains in more details the meaning of this file and the functions used in this file. A link to that tutorial is given in the description below this video. Don't forget to save that file and you can safely close it. We are at the step number 6. We need to make the final adjustments and to run the model. First of all, we need to add the dependencies. Our model will depend on several packages, and we need to tell to the build system what are these packages. So let's do that. To do that, we first need to go to this folder, and in the folder we need to edit this file. We need to add these lines to our package file. Let's do that. Where is our package file? Here it is, and over here, for example, after these lines, you can simply add executive dependencies. Our model depends on joint state publisher, robot state publisher, Gazebo ROS, Xacro, and this package, ROS GS bridge. This package is used to bridge our keyboard with our controller and with our Gazebo model. Okay, so let's save this file and let's close this file. Perfect, and let's continue. Then we need to adjust the CMakeList file. We need to tell to ROS2 where are the important files. Our important files are in launch and in the model folder. So let's do that. Go back to the terminal, navigate to this folder, and inside of that folder, edit CMakeList. Okay, you need to enter a few edits over here. What are the edits? Above the line build testing, you need to add this. This is very important. If you don't add this, the complete model will not work. So let's go back to the file and let's find build testing. Where is build testing? Here it is. So before we need to add this, install. And what are we installing? We're installing directories, launch, and model. And that's it. And where is the destination? Share project name. This is very important. So save this and close the file. Okay. And finally, we need to perform one final build of the workspace and the package. So let's do that. To do that, we need to go to this folder, and inside of the folder, we need to call our famous function _build. So let's do that, and let's hope that everything will be fine. Okay, looks good so far. After we build the workspace and the package, we need to source the setup file of our package, and we do it like this. Okay, After we do that, we can actually run the model in Gazebo. And this is how we do it. ROS2 launch mobile robot, name of the package, and the launch file. Here it is. So let's press enter and let's hope that we will not see errors. Let's see. Perfect. Now, here is the model. However, go back to the terminal and carefully analyze everything over here. You shouldn't see an error. So let's see. We got all the segments. Body link, dummy, wheel 1, wheel 2, wheel 3, wheel 4. Make sure that this is correct. We have the entity started over here. This user warning is actually not important, so you can ignore it. Waiting for service, calling service, successfully spawned entity. Okay, this is very important. And you have skid steer drive, and you have these values. You can see that we are subscribed to the specific topics and we are able to send messages. So congratulations. Step number 7 is to control the robot by using keyboard keys. Here it's very important not to close this terminal. We use this terminal to start our Gazebo. Don't close this terminal. Open a new terminal. This is very important. And in this new terminal, source the original ROS environment. Here we are not sourcing our package, we are sourcing the original ROS environment. So let's do that. Next, you need to run this node. This node will actually read the keys pressed on the keyboard, and through an appropriate topic, it will send these values to our Gazebo. So again, keep in mind, this node will actually read the keys pressed on the keyboard and it will send the key values to our Gazebo. So let's do that. Okay, now we are running the terminal. And in this terminal, we are running a node that will read the keys. Perfect. So how to control the robot now? You can minimize this window like this, and over here you can open Gazebo. Then you can also change the size of this screen such that everything fits nicely. To move the robot, this terminal should be active, so you should click over here and expand this window so you can see the keys. So let's move the robot. Click over here on this terminal, and you can press, for example, I to move the robot. Press K to stop. Then you can, for example, press L. The robot will rotate like this. Or you can press J. The robot will rotate like this. Or you can press the keys. K will stop the robot. And that's it. Simple as that. Step number 8 is an optional step. In this step, we will learn how to investigate topics, messages, etc. How to do that? Well, to see the list of topics, let us expand this window over here and let's open a new terminal. In that new terminal, first you need to source our environment. This is very important. Then, to see the list of topics, you need to run this ROS2 topic list. So let's see what's happening over here. Aha, we have command velocity, joint state, odometry, parameter events, etc. Perfect. This is very nice. Let's see the messages that are being sent through the specific topics. To do that, we need to type this. In this case, I actually selected the topic odometry. So let's see what's being sent through the odometry. And I will press Ctrl C to stop the execution of the communication, and we can see, we can see twists. We have linear and angular. Perfect. And that's it. You can also investigate other topics by using the same principle. For example, we can obtain more information about types of messages that are being sent through a specific topic. For example, if we want to see this command velocity, we can see that we are actually sending twist through this topic. Okay, that's all for today. I hope that you like this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.